Hi, getting started with something like FPGAs for the first time can be quite daunting. So I thought I might share my experiences with you as I start using them for the first time. Now I intend to get stuck in using this Elbert S7 development board that I got from Numato Labs. I'll explain later why I chose this particular board. My plan is to do a short series looking at Numato's practical examples and also a few efforts of my own, I think. Now today I'm going to focus on a quick overview of the board and the documentation, and then I'm going to install the development environment. I'll work through a simple example. I'm going to do that completely from the starting point to getting it permanently installed on the hardware, but I'll try and show the distinct stages, illustrate the tools, and also explain the Verilog as we go. Now, if you're more interested in the coding, or you're using a different board or a different manufacturer, then feel free to skip ahead. I won't be upset, well, not too much. Anyway, each topic is shown in the contents, so feel free to browse. So here's the Numato Labs website. So I bought my board from them. The easiest way to get to it is to go across here and choose Spartan 7, which is the chip type. So the AMD Spartan 3 and Spartan 6 may seem appealing because the chips are quite capable and they're available from DigiKey and things like that for not very much money. The problem is the current program in Vivado will not support them. Anyway, Spartan 7 is what we've got, so I'm going to click on that. Here's our development board, and we'll just click on View More. This is the easiest way to get into the start of the documentation for it, I find. So this is an overview of the board, and there are loads of peripherals, including some not listed here, in fact. And these are mainly why I chose the board. You don't want to over-focus on the FPGA. Obviously, you want one that's competent and adequate, but remember it helps if there's something similar on the board to the things that you're going to be using. In my case, I really wanted DDR memory and HDMI, and all these other things are actually quite a good bonus. This way I can focus on the FPGA code that I'm making, make sure it works, and I know I've got a working hardware reference design for the high-speed electronics, which is actually quite difficult in its own right. Further down the page, we've got some downloads. We've got the user manual, always good. We've got a handbook. I think the handbook and the user manual aren't that different. The handbook is basically a PDF download. There it is. So you're going to want to download that. I'll look at the manual for the moment. Got all the same stuff as that handbook. Got, let's say, for example, let's say the audio jack. Got a little diagram of the audio jack with its pin out on the actual Spartan FPGA, and also the type of connections it has and the chip that they've used for the audio. And it's the same with everything else. We've got little simplified diagrams. So that's really, really handy because that's one of the things you end up trying to look up, which is, okay, I want to use the micro SD cards. So what pins is it joined to? What's the protocol? And it's all there for you. Further down, we've got some schematics. So here's our schematics. Use those as we need them, really. They've got everything on there. It's the full board. We've got our constraints file. So constraints files, well, they do various things. So here's our constraints file. So we can see it starts off by, it sets some voltages. And then we've got our clock defined. And if we look at one of these definitions, you see it's got a package pin. So it's saying what pin on the FPGA. And we've got its I/O standard. So low voltage CMOS 3.3 volts. It's slow and fast. We've got the port to which it is connected in our Verilog or VHDL program or whatever it is that we are using. Of course, we can edit this. We can give it any name we want. We can call it system clock or something like that if we prefer. And further down, of course, we've got all the other peripherals that we were just looking at. There's also this file which shows signal and route lengths. So at high speeds, the length of connections will affect the synchronization of signals. DDR memory, for example, maybe runs at 660 megahertz on this FPGA, but at double data rate, any skew between data lines of just a few tens of picoseconds can be enough to ruin your day. So using these lengths, we can understand how to manage timing and delays to keep everything within permissible time constraints. Anyway, more on that in a later video. Over on the right hand side, we've got the knowledge base. I'm going to have a look at these first two examples. So these are just a NAND gate. Now, you know, that's so trivial that you would never put one of those in your little development library. What it really shows us is how to build something that's so simple we don't have to worry about it working, to run it in simulation and see it, and then also then to implement it in the hardware and see it using some switches and things like that. So that's what I'm going to do in this, and I'll talk a little bit about definition language as we do it. So we're going to need a development environment, and it will be a combination of Vivado Design Suite and Vitis from Xilinx. They're now AMD, of course. It's all in one download, which is shown here. I'm going to cover this in summary only because the exact details are going to vary depending on your operating system, what you've previously installed, what optional bits you might want, and whether in fact even you've got an AMD account and so on. But in summary, you need to get an account, get a download. You probably need to do an export declaration unless you're in the US. You need to get a license and then you're going to install the software. Probably AMD will then send you another license that you need to install, and then you need to install a board package if there is one for your board. And finally, you can actually get on to do something. Timed it, it took 3 hours. Okay, let's get started. So get to this page, make sure you've got the latest version selected. Now you need to scroll down and click on the download link for your operating system. And this is the same as everyone else. Either log in or create an account. If you're new to AMD, fill in your details and email. Confirm using the code they send to you, and don't forget your password because you're going to need it for licensing. Having jumped through all those hoops, you might now get an export declaration, which might also fill in from your account, but finally you get to press the download button. So download it, verify the signature if you can, and then run it. Seriously? Another username and password? And now you can have the fun of trying to decide whether to tick Vitis or Vivado for your download. You can always kind of add the missing bits later. I went for Vivado and got most of Vitis along with it. So take your pick. On the next page, ML Standard is the free version, which supports slightly less FPGAs than the enterprise version, which costs an arm and a leg. And now, of course, pick your various optional packages and make sure you do pick the one for your FPGA, because otherwise it's not going to do very much, is it? I've picked quite a bunch of them, but of course the more you pick, the bigger the download, and it can get really, really big. As well as the proprietary stuff, there's a whole bunch of third-party and open source material included in this IDE. So yeah, lots of license agreements to read and sign. So finally, you can choose where you're actually going to store it. And I would make sure you put it in a path that doesn't have any spaces in it. Otherwise, you can be causing a few problems for yourself. It will give you a summary and you can get it installed and then go for a cup of tea and a 3-course meal. Because today, the actual servers were running really slow. It took over 2 hours to download and install. So next you need to do the licensing. Now I've skipped that bit because it's full of private data and I've gone on to look at the first example. Now immediately I've discovered I need to download a board package. That takes me to GitHub and I downloaded the zip file, and then you have to of course expand that and copy the folders into the Vivado installation. And the instructions are actually in the README. While you're at it, download the manual, the constraints files and all that sort of stuff as well. So finally, 9 minutes into the video, I actually get to cut the code. I'm going to work through this example, but what I'll do is I'll just show you it directly in Vivado and just talk about the example as I go along. So we can see the icons installed just here, and I've just kicked off Vivado. So I'd normally do this for my 4K monitor, so I've got loads of space to lay out everything for development. I'm running on a smaller monitor this time so that hopefully the text appears bigger on the YouTube video. So I might struggle a bit. So the first job is to create a project. So we'll just go through and I'm going to call it NAND. Put it into MOR video. It's fine. So now it wants to know what sort of project we want to make. So RTL register transistor level. So this is all about defining behavior in terms of, you know, flip-flops and stuff like that. And it's the level that we want because we can do everything within this level. Further down, we've got things like, you know, we've built something in the past and we've synthesized it, and we don't want to go through that very, very time-consuming step again. We just want to reuse it. So they're for things like that. Next. Now, next it wants to know what we're actually building it for, so what the chip type is. So we could find the chip on here and we could use that. But actually, we get a bit of free information if we use the boards, which we just installed. So if I go to vendor Numato, and this gets updated from time to time, and you can kind of refresh it and it'll add more boards in. So there's Numato, and then we'll just scroll down a bit, and there's the one that we're interested in. So the Elbert S7, a little picture of it just to be sure, tells us how many pins it's got with board revision and all that sort of stuff. Finish. Okay, and it's going to set up the project for us. So here we go. Here's our empty project. Quick overview of what's what here. Then obviously we've got the normal menu bars and toolbars and things at the top. And down the left-hand side, we've got something that they've called Flow Navigator and Project Manager, just to kind of help us. So the project manager has got settings, sources, language templates, IP catalog. So this has got pre-built stuff in it. And IP integrator, so we can take stuff from the IP catalog and we can integrate it with our design. So let's say, for example, look at that later with a soft processor where we'll pick one out of the catalog and just use it. Simulation, hopefully that's self-explanatory. That enables to simulate the FPGA running our code. And these are the bits we're going to use mostly. So RTL analysis, this is where it looks at what we've written in Verilog or VHDL or System Verilog, takes a look at it and tries to make sure that everything's okay. We can elaborate the design and see what it thinks we're actually trying to build. We can run the synthesis. So what this is going to do is it's going to turn it into components that it actually has on the FPGA, so stuff that it's actually going to be able to use to build what we want. So the analysis is going to do flowcharts that we understand and with common components that we're used to, and the synthesis will turn them into things that exist on the FPGA. But what it won't do is it won't route all of the, won't route everything to pins, and it won't do all the actual layout onto the actual fabric of the chip. That happens in the implementation stage where we take the synthesis and we lay it out and interconnect everything properly using real stuff that actually exists on the hardware. And then we come down to the bit stream, and this is where we turn it into the uploadable file that we're going to load onto the FPGA. And further on from that, what we're actually going to generate for the flash so that we can just turn the thing on and it loads it. So, okay, so that's that. We've got a source pane. This has got libraries, compile order, and the usual sort of layout of a project. We've got a properties pane with nothing in it at the moment. And on the right hand side, we've got our big working area, which currently is showing a project summary and a dashboard. Now, this is actually quite useful because it does include things like the current status of the project, whether it's building and things like that, and also some reports on power utilization and things. And we can actually switch to the dashboard. And we just get that sort of timing utilization methodology, power, and so on, just laid out there for our convenience. And we can add other things to there if we want to. So let's actually get on and get some source into this. So I'm going to pick the design sources folder just here. We've got design sources, we've got constraints, we've got simulation sources, and we've got utility sources. So next one on, so we'll add. And it's telling you that you can add three types of things: constraints, design sources, or simulation. So obviously we're going to go for design sources. And I'm going to add one called NAND gate. So I'm going to create a file. I'm going to call it NAND_gate. Don't use a minus in here because it will not be able to understand what's going on. Use an underscore, that's fine. And I'm just going to store it locally to the project. It's fine. And there it is. There's the file. And we can create multiple files simultaneously. Once I've finished creating my files, I click finish. What it's going to ask me now is if I'd like to define some inputs. I don't have to do so. I can type them in later, but I'll do that. So comment to a NAND gate, we've got A as an input, B as an input, and we have Y as an output. So that's a fairly common layout for a piece of, just discrete logic, really. Let's click the button. And it won't open it for us, unfortunately, but what it does is it puts it in design sources. It's got a 1 after it now. So we'll go into there and we'll double click on it. Now I need to actually see what they would like me to pop into this. So in fact, I'm going to take that out again just so that we can see. So you can see that, for example, it's indicating some errors on the screen for us live. And it says error procedural assignment to a non-register. Well, okay. So actually, let me just put reg in there and turn Y into a register. So there's two types of logic really that we're interested in. One is combinatorial. So things like inverters, AND gates, NAND gates, and so on are combinatorial. So you put inputs in and the output just comes out. There's no clocking, there's no storing. Change the input, the output changes and follows suit. It's just a few transistors in between the input and the output. And then we've actually got register or clocked type things. So these are things like flip-flops where you apply an input and then it latches that input in and stores it on the edge of a clock. To do that, we obviously have to work with a clock. We don't have a clock here. So by definition, we are actually going to be doing combinatorial. Up at the top, we've got what's called the port. Think about the wires on an actual NAND gate chip. These are them. These are what you're building a circuit, don't forget. So A, B, and Y are actually the connections to that circuit. They're all that anything else can use. These can be inputs, they can be outputs, or they can be bidirectional input and output. If we look at output Y, we're saying this is a register. Although Verilog has all sorts of variables. The synthesizable things, particularly the ports, are pretty much register or wire. All the ports are wires unless they're explicitly marked with reg. Now I like to think of the difference between register and wire like this. A wire permanently joins things together. Only one thing can output voltages onto that wire, but many inputs can be connected to see what's on it. The value on the wire reflects whatever output it is connected to. It doesn't have a value of its own. A register, on the other hand, does hold a value, and that value can be changed procedurally in your Verilog. You might join registers to other registers using a wire. Now, registers are not necessarily latches, but if you do connect a clock to them, then they will become latches. So wires and registers can be arranged singly or in buses, and they may be connected to constant values as well, like ground, to represent logic. Using a register for the output of a NAND gate is a bit overkill, but I guess they want to demonstrate the use of procedural blocks, which are very prevalent and of course good practice for everything other than gluing little bits of things together. Now, NAND gates and such like are built into Verilog, so we could just join wires to them, and I'll show you that shortly. This is the start of a procedural block. We are using a C-like procedure to describe the behavior of the circuit to be built. So it's helpful if you, when you're sort of reading this out to yourself, if you sort of include the words a circuit that or circuit in which. So always, and then this at star is what's called a sensitivity list. So when something happens, well, when anything at all happens, the star is a wildcard for anything. So always, when anything's happening, let's use a circuit in which if A and B are both high, Y, the output, is going to be set to 0. Otherwise, Y should be set to 1. So that is the description of what's in here. We just need to make sure we understand in our heads that we're describing the behavior of a logic circuit. We're not describing a piece of code that runs sequentially. So begin and end are just like block markers. In C, you would use braces, but we use the word begin and end, and they appear in lots of places. If you do an if statement, you can do a begin and an end after it if there's more than one line. But yeah, there we go. So let's have a look. Let's save it first of all. And what I'm going to do now is I'm going to run this linter. So this is just going to do some basic syntax checking and things like that. Make sure it all seems to be okay. And it's finished and it says no violations. So that's always a good start. Now, something I can do, which is quite interesting, is I can go down here, I can open the elaborated design, and it will tell me various things, most of which won't have anything in them because this is so simple, but I can click on schematic. Now, what it's telling me now is that we can perform I/O planning and stuff like that, and it will create constraints files for us. We're not going to do that for the minute. That means we can kind of connect, for example, A and B, we could connect them to actual pins on the chip, but this is not necessarily the best way of doing it. Okay, and here we have it. So here's the design that it just created for us. So if you think about what we asked it to do, we asked it to look at A and B, and if they're both the same, we want it to be a 1, and if they're not both the same, we want it to be a 0. So the output from the AND gate that it's put in here in the circuit diagram can either be 1 or 0, and that's going into, let me scroll up a bit, into this multiplexer. Now, input 1 is connected to the constant 1, so it's connected to VCC essentially, or input 0 is connected to ground, and input 1 is connected to VCC. So that's our 0 and our 1 that it's going to choose between. So it's using the output, the AND gate, to choose between 0 and 1 and output them to Y. So that's fine. That's a perfectly understandable diagram of what we just said. And this is all combinatorial. There are no clock signals in here. There are no flip-flops. Let's have a look and see how it's actually going to build it in the chip. And if we look at the top, by the way, we can see it's going to use 2 cells of the 65,000 that we've got on the chip. It's going to use 3 I/O ports. That seems to make sense. And it's got 6 nets. The nets are just like on a PCB or a circuit diagram. They are the wires between everything here. But you do have a limited amount of nets available in the FPGA, but it's many, many thousands. Okay, and the other thing we can do is we can actually look at an input, let's say for example A, and we can look in the I/O port properties and it tells us some stuff about it. It's got an I/O standard of 1.8 volt CMOS, and it's got a name, etc, etc. It's unconnected, and of course we could actually configure it and connect it to something. It hasn't got a pull-up, and it's got an I/O standard, and so on. So all those things are editable in here. The instant you do, you will start creating new files to store all that information that you are adding. So those will be called constraint files. Okay, so let's have a look at this in the synthesis. We come up with here, and I can run 16 threads, and the synthesis is heavyweight. It takes a lot of processing. It's doing a lot of work, and I'm going to cut the video short here just to skip this bit. Okay, our synthesis has completed, and now it wants to know whether we want to run the implementation, which is of course the next step that we would normally do. I'm going to cancel out of that. And by the way, the synthesis, it says at the bottom, took 15 seconds. And you know, it's one gate. So keep that in mind, that when you start building complicated things, that time is going to increase quite a lot, at which point you might want to build building blocks, do the synthesis, get them working, store them away, and then just include the synthesized building block rather than all the Verilog. Anyway, let's move on and have a look at a new schematic then. So what we're going to do is look in the synthesis section, open the synthesized design, and there's a lot more in here, as you can see: clock networks, interaction, noise, utilization power, and so on, because now it's got some idea what it's actually really building. I'm going to click on schematic in here, and the schematic looks a bit different. Before we had an AND gate and a multiplexer, and now if I come to synthesis, it's saying, no, actually, I don't want to do it like that. What I want to do is I've got an input port. I'm kind of assuming that it's connected to a pin, so it's going to go through a buffer. And what it's going to do then is it's going to go into a lookup table. So the lookup table has got two inputs, input 1, input 2, and it will look up one value based upon all the 4 possible combinations. And that goes to an output buffer and out to an output pin. Okay, let's run the implementation now then. So this is actually going to have to put it somewhere onto, did I run that? I think I did, yes I did. It doesn't give you a lot of feedback. So just down here, I've switched to design runs, and it's got a little circle down here just telling me that it's actually running, and it will tell me the elapsed time as well over on the right hand side. So what it's going to do is going to take that lookup table and the buffers, and it's going to place them somehow on the chip. Now, since I haven't told it what pins I want, it will choose 3 for me. Okay, so let's open the implemented design this time. So what it's doing now is it's showing us the fabric of the FPGA. If I zoom in a long way, it's kind of like blue cells. Well, these are all the little cells, interconnects and everything that exist in the FPGA. And if we look down here in the bottom corner, this is where it's implemented our design. I've zoomed in on this quite a lot. And over on the left-hand side, we can see that there are 3 pins, U11, V12 and R12, and their associated buffers. So I'm just going to zoom in on that quite a bit more. Let's just do that. There we go. And if I hover over this, you can see that that's site U11. It's a pad, and it's got some information about it on there. And if I go here, it says this is an output buffer. So this is the Y output buffer. Come down here, V12, this is an input port B. It's also a pad, it's on V12. And just here, we can see that there's an input buffer. Now, I can actually zoom in even further, and we can see what's going on with these buffers, even what their connections are. And if we follow this input buffer along, we can see that we've got all these components here that actually aren't used in this instance, but there's output logic, then there's input logic. And if we kind of take a little look at that, we've got a shift register here and 2 shift register inputs and 2 shift register outputs. And then we've got our serial to parallel conversion happening here with these actual Q outputs. So this is going to do things like serializing, deserializing, dynamic clock selection, all sorts of stuff that you might want to do on that pin. And across to the right then, we've got a delay line. So we can actually delay this pin by, delay the signal on the pin by, picoseconds as needed to synchronize it with other things. If we continue along across to the right a little bit, let me just zoom out a bit so I can find the right site. So just up here, we can see that there is just one of the lookup tables in slice X0Y1. And there it is. It's not really showing us our connections particularly. There it is. It's our lookup table, cell Y, OBUF inst I1. So let's go and have a quick look at the schematic again. And there we go. You can see that there it is. Y, OBUF inst I1. Okay, so having got our NAND gate to actually compile, so to speak, to synthesize and to be implemented, it would be a really good idea actually to simulate it to make sure that it's actually doing what it's supposed to be doing. Very easy to make a mistake. I mean, all we have to do is change Y equals 0 to Y equals 1 just here, and it's not going to be a NAND gate anymore. So let's look at simulation then. If we look on the sources over on the left hand side, we can see that we've got a design source, which is the NAND gate that we've just written. And we can also see we've got a simulation source, which is also the NAND gate. It's not saying that it's going to directly simulate it. What it's saying is that's available to be used for simulation. And if we actually look down at the source file properties just below we can see that it's used in synthesis, implementation, and simulation. So of course, we can exclude and include things into those various different stages. So what we need is a test bench. Normally, when we actually implement, if we put this NAND gate on the chip, we'd normally want to put it in some sort of top-level container. Something would use the NAND gate. It wouldn't just sit there all on its own, usually. Could do, but you wouldn't normally. You'd use it in another design. And it's exactly the same with a simulation test bench. A simulation test bench is a bit of Verilog that's going to instantiate a NAND gate and send it some signals. It's going to describe a sequence of signals we give to the NAND gate, and we'll then be able to look at them on kind of like a little logic analyzer type thing, or we'll be able to display values onto a log in order to see what's going on. Anyway, let's have a look. Here we go. We'll do what we did before. So we'll add a file, but this time we're going to add or create a simulation source. Next. And it's quite important to do that because we're going to use some simulation directives in here, which would not necessarily work very well in a normal file. We'll create a file and I'll call this nan_tb for test bench. This is a top level test bench. It isn't connected to anything, so there are no inputs. And if we look at the source pane now, we can see that we've got both a NAND gate and a NAND test bench. Let's open that up. Okay, so our example on the Numato website does have some code that we can put into this, and it's not necessarily quite what I would write. I'm going to paste it in bit by bit and just talk about each little segment as I paste it in. So here we go. First of all, we need some signals that we can send to our NAND gate. So we've got here a reg A and B, we've got a clock, and we've got a wire Y. Well, you recognize, I think, from the NAND gate that it has inputs called A and B, and it's got an output called Y. But also we've got a clock here, so why is that? Well, it's because we want to meet out time in our simulation. I don't think we actually really need it, but it does give us a nice handy clock signal when we actually do our simulation, so we can kind of see time very intuitively. A and B in the NAND gate are actually wires because they take their input from something, they're permanently connected to it. But in here, A and B are registers, and that's because we want to sequentially give them different values over time. So they've got to be registers because we're going to assign values to them. Why can Y be a wire? Well, because it's connected to the output of the NAND gate. It connects the output of the NAND gate to our simulation environment. That's it. So a wire. I'm going to ping the clock source in next because I mentioned the clock. So here's our clock generation. So clock is a register, so we can use an initial to set it to a value at power on. So we're going to set it to 0. Initially the clock is 0. And then always #5. Well, this always is therefore a procedural block. We know that. So every 5 somethings, so 5 watts. Well, up here at the top, we can see there's a timescale defined. This is a directive, and timescale is 1 nanosecond, 1 picosecond. Now, this is only going to affect simulation. It will be on most of the files, but it does nothing other than in simulation. And similarly, this #5. It's just a simulation directive to say simulate waiting 5 whatever time units we're using. The time unit we're using is 1 nanosecond. So every #1 down here is 1 nanosecond. And display my results at a precision of 1 picosecond. So here, every 5 nanoseconds, we assign clock to equal the inverse of clock. So switching it backwards and forwards between 1 and 0. And it does it endlessly. Now we'll look at actually putting our NAND gate into place. Here it is. So my NAND gate isn't called NAND gate, it's called NAND. So let's just change that. So NAND UUT. So it's creating an instance of a NAND gate and it's calling it UUT, unit under test. And you can see here that in the brackets, we've got our port assignments. So to UUT port A, that's what the .A means, port A, we're connecting that to A in our test bench. So just to make that clearer, I'll call that TB_A and TB_A here. So we're connecting port A of the unit under test to the test bench A, and then to B and to Y as well. So I'm going to just change that back to A and B. That's our AND gate created. We can create as many as we want. So let's actually look at sending some signals then. So here's our stimulus. So we've got initial begin. This is actually going to set the value of A and B. So registers should always be initialized. In this simulation, we don't do anything other than initialize them to a sequence of values. So I've chosen to do the initial begin and to list out all the separate things. And if we look, we've got A equals 0, B equals 0, and then a pause of 10 counting units. And then we change the value and then we pause and we set it to something else and so on. And that's sort of all right if you've only got 2 inputs, because there's only 4 combinations, it's absolutely fine. But if you've got 16 inputs, that's a lot of combinations, isn't it, that you'd have to list out here. So you probably don't want to do that. So you'd probably actually want to write a bit of Verilog that would make it a bit smarter and shorter. I'm not going to cover that in this video, but I will perhaps pick it up in a little video later where I perhaps just go through 1 or 2 of the bits of Verilog and explain a few things and demonstrate a few beginner bits and pieces. So having gone through the sequence of 4 things with a pause of 10 nanoseconds in between each one, we then finish the simulation. $finish is a directive to the simulator to say, I'm done, stop the simulation. We can use $stop instead, by the way, which will essentially pause the simulation and then you can pick it up again. So you might look at these 4 and then you might put something else in, do some more tests on that one, and you could do a $stop in between them and essentially look at it in little segments at a time. So let's save this. We'll actually go across and we'll click the Run Simulation button. Okay, and it has run and conveniently closed the screen for us. So here's our simulation. Let me just make it a bit bigger so we can see it clearly. And what I'll do now then is I'm going to click this button just here, which is Zoom Fit, because if we look at this, we can't really see what's going on. It's showing us picosecond resolution, which is what we asked for. But of course, most of the display is off the left-hand side. Let's zoom to fit, and we can see our pattern here. So the top 2 are A and B. And if I click on one of those traces, it gives me a cursor I can move along. And the value over here next to A and B will kind of change to keep track of what's under the cursor. So you can see the clock, the 3rd line down is the clock, ticking every 5 nanoseconds. It goes up or down. So that's a 10 nanosecond period. So for the first period, we've got A and B both equals to 0 and the output is equal to 1. And then we go to 0, 1 and the output's still 1. And then we go to 1, 0 and the output's still 1. And then we go to 1, 1 and the output Y becomes 0. And that is precisely what we would expect. Keep zooming in. So we're not actually seeing anything like the timing of the propagation delays and things like that in here. So if you want to actually model the delays, what you need to do is actually run it against a file as though you were going to implement it on the fabric of the FPGA. So we have to go through the synthesis and the implementation steps first, and then we can go to Run Simulation. And you can see that there are synthesis, post-synthesis timing simulations and post-implementation timing simulations. Since I run the implementation step, I'm going to use that latter of the 2. And so it does exactly what it did before, but we should be expecting some slightly different outcomes. Kind of looks the same so far. If we zoom to fit, then we can see that it's actually quite a bit different. So the first thing we can immediately see is that the Y, the output of the NAND gate, is actually invalid for quite a long period. So if I do what I did before, put a cursor in, we can see the output is X. So it could be either 0 or 1. The simulator can't decide. And it stays like that until 6.18 nanoseconds, thereabouts. Propagation delay of that actual gate. We're setting A and B both to be 0 at 0 nanoseconds. So that's the first signal that that gate actually receives. And it doesn't become valid as an output until 6.18 nanoseconds. If we looked at the timing reports and things like that from the implementation, we would find the same figure in them, and the setup and hold times would be defined. So we can see the same thing sort of happening. The clock is perfectly timed, of course, because that's our sort of benchmark, if you like, and we're pretending we've got a perfect signal coming in exactly on the clock. But let's scroll across and look at the last bit. So at 30 nanoseconds, we change the A and the B input to be both 1. Now, at this point, of course, the Y input should drop down to 0, but it hasn't done so. It's holding on, and surprise, surprise, it doesn't drop for another, well, 6.155 is what we're measuring. At this instance, we could zoom in, I suppose, see if I'm on the line. Yes, I am, because we've got picosecond precision, of course, and that's why we've got it. So we can see things like these propagation delays. It's not that much use in the behavioral analysis, but in the timing simulation, it's pretty good. So there we go. We can actually model the propagation delay of that gate. Okay, so the job now, of course, is to get this onto the FPGA so we can see it running on the hardware. Now, there's 2 ways to do this. The first is to put it straight onto the FPGA. We can do that with USB or JTAG. So that's fine. It's really good for simple testing and making sure everything's working. But ultimately, we're also going to want to program Flash, and so that will be the second stage. So first stage is to get this on the fabric of the chip. Now, the first issue is actually we just let it wire it however it fancied. So now we have to tell it what pins we want to use for everything. So hopefully you will have grabbed the constraints file that I said to download. Okay, so we'll add a new constraints file. We'll create one and create a file, and I'm going to call it pinout. Will do. So there it is, pinout XDC. And we'll finish and open that file, and it's just an empty file. So if we grab our constraints file, we can of course use the tutorial and just get the bits we want, but it's nice to show it bit by bit. Control C, so I'll borrow that and paste it in. So this is setting an important voltage that's required at the start. Then I'm going to find 2 switches. So now we'll paste those in. Let's just put a few lines in. There we go. So here are our switches. So you can see it says set property, package pin C4. So this is the pin on the actual package. It's going to use 1.8 volt low voltage CMOS. It's a standard IO port, fast slewing, and it's called SW0. Now, of course, in our design, it's called A. So I could actually just replace that with A, like that, assuming the NAND gate stays right at the top of the stack of modules. But this wouldn't be the normal way of doing it. So it's nice if we can actually keep this file where this half of it refers to the actual printed circuit board, so the schematic and perhaps the legend that's on the silk screen of the board. It's the hardware that we're driving on the right-hand side of this, and on the left-hand side of it, it's actually the FPGA. So it's nice if we can keep that mapping visible in here, because otherwise it's very easy to just lose track of where we are. Now, in the Numato example, it actually just uses one LED, which of course it connects directly to Y, but I'm going to bring in 3 because I would like to wire up an LED to each of the switches, so that when you switch 0 on, it actually shows it on an LED. It's just nice to have that extra bit of visibility. We've got 8 LEDs to play with, so why not? Let's just do that. LEDs 0, 1 and 2. So LED 0 and 1 are going to be connected to switch 0 and 1, and LED 2 is going to be connected to Y. And now then, I just need something that will link these little pins onto the NAND gate. So just like we did with the simulation, create file. So I'm going to call this top level because that's what it is. Finish. Of course, these LEDs and switches are all inputs and outputs. So I can actually do them in here. SW for switches, because that's what it's called in the constraints file. You can see it behind. It's an input and it's a bus with the most significant bit is 1 and the least significant bit is 0. And now I want an output, which is the LEDs. That is also a bus, and there are 3 of them, so the top most significant bit is 2. There we go. So I'll click OK on that, and hopefully in a second, yeah, there it is. Here's our top level, and we can already see, in here that we've got our switches and our LEDs defined. They are inputs and outputs, and this is just like any other module. There's nothing special about it at all. So the first thing I want to do is I want to connect the wires between the switches and the LEDs. I'm going to connect LED 1 through 0 equals the switch 1 through 0. So there we go. That's the LEDs wired to the switches. So now I just need to deal with my inputs and outputs to my NAND gate. So just like in the simulation, I need to create an instance of it. So NAND, so I'll call this my NAND. And then within here, I just need to put my port mapping. So port A on the NAND is going to be fed by switch 0. Port B on the NAND gate is going to be connected to switch 1, and the Y port on the NAND gate is going to be connected to LED 2. Well, I think that's it. Because literally in this top level, what we're doing is wiring our components together to integrate them into a whole design. So there we go. So let's save that, and we'll just run the linter on it just to be on the safe side. So our synthesis and our implementation are both going to be out of date, and it actually tells us this on the design runs down at the bottom. And of course, the reason for that is that I've just introduced a little bit of extra wiring for a few pins. And of course, I've put a constraint file in, which tells it has to use specific pins, which it wasn't using before. So definitely things are going to be a little bit out of date. So we've got synthesis and implementation. So we need to run those again. But I'm going to take a bit of a shortcut. I'm going to come straight down to generate bitstream. And it says, is it okay to launch the synthesis and implementation first? Absolutely. So here we go. Now it's telling us it wants to launch the runs. So down in the design run section, it's telling us it's now running synth design. So here we go. The bitstream has generated successfully. So we've got various things we can do. We can open the hardware manager, which will actually be the next thing, but we can also view reports. We can do that. And down here, a whole load of reports. So timing reports, power reports, routing, and goodness knows what else. But we want to get it on the hardware, don't we? So that's our next job. We'll open the hardware manager, which is just here. And it's the only thing available is to open the target. So we'll do that and I'll auto connect. Okay, and there we go. So you can see up here that it has identified the board. It's found a program chip, which is the XC7S50, which is the chip on the board. And it's also found, because it's a JTAG interface, although it's going USB, it has actually also found the ADC system monitor. So there we go. So the temperature is 55. There's our VCC and video and etc. etc. So yeah, so that is working and it's communicating as it should do. Let's go and program the device. So on the left hand side here, we've got the target open. Now program device and add configuration memory device have both appeared. So let's program the device, XC7S50. Okay, so I'll warn you that I'm shooting the video of the actual device itself on the mobile phone because I'm just in my office and the lights are off so that we can hopefully see these LEDs quite clearly because they are quite faint. Yeah, I'm going to hit the program button and fingers crossed. There we go, the device we want. There's the file that we want and we just hit program. And you can see the board has already changed to running the actual thing that we're interested in. Now, here are my switches. So the two switches on the left, they've both got the little light next to them. And we can see that both switches are on, the two lights are on, and the third light is not turned on at the moment. So let's turn one of them off. So now we've got the input of 1, 0, and the output is 1. Now we've got 1, 1, and the output is 0. 0, 1, the output's 1, and 0, 0, the output is 1. So that is perfect behavior of a NAND gate. Now the only problem now, of course, is that if I turn the power off and turn it on again, then my program is no longer there. And in a few seconds this will reboot back to the demo program. So there we go. So next job is to learn how to program the actual flash chip. So unfortunately, the tutorial that I was following doesn't actually cover this rather important topic, so I had to go across to the handbook instead. So not too much of a problem, but yeah, a bit sad it didn't include it in the actual example that it was given, because it is pretty fundamental. So what we need to do is we need to choose our actual target. So I've got the hardware manager running, I've got the programmable target already selected, and I'm going to click on add configuration memory. Now I can actually right click on here and do it up here as well, but I'll click down here, add configuration memory to the XC7S50, and it comes up with a whole raft of possibilities. So what I need to do is follow the manual and make sure I get the right one. So apparently mine is made by Micron, MT25. So I want to look for MT25QL28. And it says I want the 3.3 volt one, which is lucky because although the picture in the manual shows two devices, well, this only has one device available. So yeah, I'll pick that one then, shall I? We can narrow it down, of course, by choosing it's 128 meg. So anyway, we've only got one match for typing in the part number. We'll click OK. Well, that's good. Do I want to program the configuration memory now? Yeah, okay, I guess. It says browse to the bin file. Well, where is the bin file then? Where is it? Where is it going to be? So after searching for about 5 minutes, I came to the conclusion I didn't have one. So I'm going to have to explore around, I guess. Here we go. I reckon it could be this one up here. Generate memory configuration file. I'll do it as a bin file. Well, let's give it a file name, shall we? And hang on, I can pick memory part there. So that's good. And we'll give it a file name. We'll call it, what should we call this? NAND. Funnily enough, I think that would be a good name. Interface SPI X4, I think, is correct. And I'll click OK. I've got 1, 2, 3, 1, 2, or 4. And the memory says it takes 1, 2, and 4. So yeah, 4 sounds good. Use at least 1 bit stream. Okay. Where do I choose the bit stream? Oh yeah, okay, there we go. Load bit stream file. So where's my bit stream then? Come on, NAND gate. Where's the bit stream? Is it in our hardware? No. I mean, a clue would be nice, wouldn't it, really? Top level bit. There it is. It's in the implementation folder for some bizarre reason. So I think that's it. I think that's correct. I have no idea. Butts width is set to 1 and it has to be set to 4. Make sure you set a valid value. Well, why did you let me set an invalid value? Because it hasn't, on here, I've got no control over that width that it was talking about. So I'll go for SPI times 1 then, shall I? maybe? Finally, I've got my file. Okay, so let's try and program that then, if I remember how. So if I right click on there, program configuration memory device, pick that configuration file again. I read what? Oh right, state of non-configuration memory I/O pins. Don't know. Leave it alone. I'm going to erase it, program it, verify it, and click OK. Okay, so it has indeed loaded on. If I turn this off and turn it on again in a few seconds, hopefully, that light will go out to tell me that it has loaded. And there it is, it has loaded. And hopefully you can see that LED 3 is lit, neither of the other two are. If I turn them both on, then switch 1 is on, switch 2 is on, and LED 3 is off. And yep, there we go. There's our normal NAND behavior. Absolutely fine, just behaving itself perfectly. So indeed, the actual load into memory has taken place as planned, but it was certainly a bit of a faff trying to find out the details as to how to do it. That should have been in the example, I think. So I must admit to being a bit surprised that it was so convoluted, and I did discover, after a little bit of experimentation, that in fact there is an option to generate memory configuration file as soon as you finish with the bitstream generation. I must have just kind of missed that in the past. Nevertheless, you still do need to know how to do it as a separate step. Anyway, hopefully that's going to save you some grief. So there we go. I think I've finished this video. I've done all that I promised, which is go through those examples, talk about the code in them, explore them. I've kind of elaborated around them, looked at many of the tools that are available to explore your own designs, finally got it onto the FPGA, and finally, after some effort, got it onto the SPI Flash memory as well. So fingers crossed it'll go more smoothly for you if you've watched this video. The next video should be much more focused on the Verilog and actually getting interesting code working, and I hope to see you there. So take care for now, and don't forget to subscribe, like, comment and share, and I'll see you soon. Bye for now.